Now next topic is addition of vectors. To understand addition of vectors, I am taking a triangle. This is a triangle ABC. See now what I am doing. This is vector AB. So vector AB. B is terminal point, A is initial point. Now in vector AB I am adding vector BC. Vector BC, that means in this direction. Here initial point is B, terminal point is C. So terminal point of first vector and initial point of second vector coincides. AB plus BC. So addition of these two vectors will be first initial point keep here and last terminal point C. So it is vector AC. This is vector AC. AB continue in the same way. BC is equal to, come on the starting point, AC. So AB plus BC is AC. This can be written as AB plus BC minus AC is equal to vector here 0 vector. If nothing is left, that means 0 vector. We don't keep only 0 because these are vectors, not real numbers. That is AB plus BC. Now minus AC. Minus AC, that means opposite vector of AC. This is AC. So this will be minus AC. It is minus AC. This vector is AC. So without changing direction and magnitude, if we reverse the direction, we are changing direction, not magnitude. This is AC, now direction is reversed. This is minus AC. So AB plus BC plus minus AC is vector 0 vector. Now minus AC is equal to vector CA. What is it? This is nothing but CA. It is vector CA. So result is AB plus BC plus CA is equal to vector 0. So move along sides without changing direction. Come on the initial point. Resultant is 0 vector. Suppose I want for this triangle PQR. So for this triangle, what we can say? Vector PQ. I am starting from P. Vector PQ plus vector QR plus continue in the same way. Vector RP is equal to 0 vector. Or this can be written as PQ plus QR equal to minus RP. Vector PQ plus vector QR is equal to vector PR. Now look here. Vector PQ plus vector QR is vector PR. This is vector PR. This is PR. PQ plus QR is PR. Initial point put here, last terminal point put here, and when you add two vectors, terminal point of a first vector and initial point of second vector coincides. So this is said to be triangle law for addition of vector. So it is triangle law for addition of vectors. Now same thing I am discussing using parallelogram. Suppose here I take a parallelogram. This is a parallelogram O A. Here I keep B, here C. In parallelogram OACB, OACB. So this vector is vector OA, plus vector AC, terminal point of first vector and initial point of second vector, keep them in contact of each other. To add them, OA plus AC is equal to, by triangle law, it is equal to OC. It is OC. This vector is vector OC. Now see, if I keep here vector A, this vector is vector B. So this will be vector A plus vector B. Now see, this vector is vector B, so this will be also vector B, because directions are same, magnitudes are same. So look here, addition of vectors. Say here vector A plus vector B is vector A plus B. A vector B, vector A plus B. Now in this statement, see, this is OA plus vector AC. Instead of AC I am putting OB, because vector AC is equal to vector OB. So AC is OB, it is equal to OC. Look at this statement. So here you can see that sum of vectors along adjacent sides, these are adjacent sides, OA, OB. Sum of vectors along adjacent sides is equal to vector along diagonal. This is a diagonal. So this is said to be parallelogram law for addition of vectors. So this is said to be law of parallelogram for addition of vectors. So whenever we want to add any two vectors, as for example, say here this is vector A bar, this is vector B bar. You want to add them. So what we do? To add these vectors, we want to add these vectors. We want to add A bar and B bar, or vector A and vector B. The procedure is, this first vector is A bar. First vector is vector A. Now second vector, without changing direction and magnitude, copy and paste here. That means initial point of vector B and terminal point of vector A, I said to paste here, not paste here, we will paste at this point, means to add them, initial point of vector B and terminal point of vector A coincides. So that means copy, paste here. So these 2 points coincide. So without changing its direction, this is B bar. So without changing direction, here I am setting vector B. This is vector B. This is vector B. Hence, without changing magnitude and direction, shift anywhere, paste anywhere, it remains vector B. So vector A, vector B by law of triangle. This is vector A plus B. This is the method to add vectors. Now properties. Properties of addition for any vectors A, B and C. Vector A plus vector B is vector B plus vector A. Vector addition is commutative. Second property, vector A plus vector B plus vector C is equal to vector A. Now put association of B and C. This means vector addition is associative. Associative property is true for vector addition. In any vector A bar, if you add null vector, that means zero vector, then result is vector A. Add zero vector from either sides. In any vector A, if you add its opposite vector, then result is zero vector. Now next topic, multiplication of a vector by a scalar. Now to understand this topic, suppose I take a vector, this vector A bar. We say vector simply vector A. Suppose I take its magnitude 1, 2, 3, 4, 5, I take 6 units. As for example, its magnitude is 6 unit, showing by 6 partitions. This is vector A. This is vector A. Now I am making magnitude its half. So its half magnitude, that is without changing direction. See here, I am copying this part. This part I am copying. So it is something like this. 1, 2, 3, and keeping same direction. So magnitude is half, direction is same. So this is half times vector A. Now if I reverse the direction, now reversing direction, magnitude is 3. This is 3, I am putting this 3 units. So whatever is magnitude of this vector, it's half magnitude, so here half, and direction is reversed, so I keep here minus. This is 6. Suppose I take another vector. Suppose this vector is vector B. Now whatever is its magnitude, I am taking 3 times magnitude of b bar. So length of directed line segment, now I am taking 3 times. 1, 2, 3. So 3 times. Whatever is here magnitude of this vector is 3 times. So this is 3 times vector b. If I reverse direction, keeping magnitude 3 times of given vector, so this is minus 3 times vector b. So say here with every vector I am multiplying a number. It can be positive, it can be negative. Say here with every vector I am multiplying a number. So that is multiplication of a vector by a scalar. This is the meaning of multiplication of vector by a scalar. So for any vector a bar or vector a and scalar lambda, here lambda is minus half, here lambda is plus half, here lambda is 3, here lambda is minus 3. So for any vector a bar and any real number, scalar means any real, lambda a bar or lambda a is also a vector. Lambda can be positive, it can be negative. So this is multiplication of vector by a scalar. Now for vectors a and b, we can take any two vectors, vector x, vector y. Properties: lambda times vector a, vector b, this can be expressed as lambda a plus lambda b. Or if I take two scalars lambda and m, lambda plus m times vector a equal to, this can be written as lambda a plus m a. Here lambda is a vector, m is also, sorry, lambda is a scalar, m, suppose I take here mu is a scalar. So for vectors a bar and b bar, scalars lambda and mu, these are properties. Then magnitude of lambda a, vector a, magnitude of lambda times vector a, magnitude of lambda times vector a is equal to modulus of lambda into magnitude of lambda. See words I am speaking. Magnitude word is for vector and modulus word is for number. Lambda times a bar or lambda times vector a, it is a vector. So over vector, this is symbol of magnitude. We speak magnitude. So magnitude of lambda times vector a equal to modulus of lambda into magnitude of vector a. So wherever I have taken a vector, I speak magnitude. Over number, I speak modulus. So as for example, suppose if I talk about minus 3 times vector b, so minus 3 times vector b is equal to modulus of minus 3 magnitude of vector b. That is, modulus of minus 3 is 3 and magnitude of vector b, suppose magnitude of vector b, it is 1 unit, or suppose here this is 5 units, This is, its magnitude is 5. So here magnitude will be 15. So if I keep here, if we suppose magnitude of vector B is 5, so magnitude of this will be 15. So like this. Then next topic is component form of vector. Component form of vector. To understand this, I am taking, this is OX, OY and OZ. Here this is a point A whose coordinates are 1, 0, 0. Here point B whose coordinates are 0, 1, 0. And on OZ direction, on this direction, suppose somewhere here point C whose coordinates are 0, 0, 1. So this length is 1. Now this OA, if I show this line segment as directed line segment, then this vector is vector I cap. It is a unit vector. This vector is vector j cap, unit vector in the opposite, in the positive direction of y-axis. And this vector OZ is vector k cap. I am speaking cap, k cap, simple word cap, because for unit vector we use this symbol. These are standard unit vectors. So in this direction, in this diagram, here vector OA, vector OB, OA is I cap, vector OB is j cap, vector OC is k cap, are unit vectors. These are standard unit vectors which we are using in vector geometry. So standard symbols for vector OA, vector OB and vector OC. Now see one more thing. Vector OA, that means unit vector in this direction. See, this is X, this is Y, this is Z, this is O. Here 1, here 2. On X axis I am putting few numbers. So in this diagram just I explained, this is vector I, unit vector along OX, means in this direction. So that does not mean that I cap is a vector lying only on X axis. See, words are I cap is a unit vector in this direction. That means if I draw here length same 1, here length is 1, parallel to X axis, vector of magnitude 1. So what is it? It is nothing but I cap. This vector, without changing direction, copy, paste, keep anywhere. This is I cap, this is I cap. If magnitude is 1, direction is same, it is I cap. So I cap, that does not mean that whatever you draw only on X axis is I cap. It is not correct. Anywhere, copy, paste, don't change direction, keep magnitude 1. So these same vector, these are not different, I cap. Similarly, for j cap, this is j cap, this is k cap in this direction. So that is from vectors. Now in this coordinate plane, not plane, in this space, suppose somewhere here I am taking a point P, this is I cap. P is a point whose coordinates are x, y, z. This is origin. Now joining origin with P, this is directed line segment. So here we are getting vector OP. Now look, if P x, y, z is any point in the space, then position vector of point P, position vector of point P is vector OP, and vector OP is represented as x times I cap plus y times j cap plus z times k cap. Position vector of a point P, that is vector OP, can be represented as combination of I, j, k. X times I cap plus y times j cap plus z times k cap. So this form of vector OP is said to be component form of vector OP. And see here, these coefficients x, y and z, x, y and z are real numbers. It can be any real, positive, negative. So these numbers which are coefficients of I, j, k, these numbers are said to be scalar components of vector OP, and xi cap comma yj cap comma zk cap, these are said to be vector components of vector OP. So look these two words, vector component and scalar components. Then see, just I discussed vector OP. If vector OP is x times I cap, y times j cap, z times k cap, then its magnitude of this vector is square root of x square plus y square plus z square. So magnitude of any vector which is in component form can be found by sum of squares of scalar components. As for example, if vector OP is 2y cap minus 3j cap plus 4k cap, then magnitude of vector OP is square root of 2 square is 4 plus minus 3 square is 9 plus 4 square is 16. So it is root 29. Then how to add vectors if they are represented in component form? say if vector A is x1I plus y1 times j cap plus z1 times k cap and vector B is x2 times j cap y2 times k cap j cap, sorry here I cap, j cap and z2 times k cap. These are two vectors, vector A, vector B. Here scalar components x1 y1 z1, here scalar components x2 y2 z2. Then say addition of these vectors a bar plus b bar, it is equal to, how to add them, x1 plus x2 times I cap plus y1 plus y2 times j cap plus z1 plus z2 times k cap. How to subtract them? Subtraction like simple, which we do subtraction in algebra. x1 times I cap minus x2 times I cap plus y1 times, so we are subtracting now. So x1 minus x2 times I cap, y1 minus y2 times j cap plus z1 minus z2 times k cap. And for any scalar lambda, lambda is any scalar, lambda times a cap, I am multiplying this vector with lambda, lambda times vector A, sorry, lambda times vector A. So multiplying this vector with lambda, so it is equal to lambda times x1I cap plus lambda times y1 j cap plus lambda times z1 k cap. So that is multiplication of any vector with scalar. So this is about how to add, how to subtract, how to multiply vector with a scalar if they are given in component form. Then say if vector A is xi cap, yj cap, zk cap, then its magnitude is square root of x square plus y square plus z square. And say here x, y and z, these scalar components x, y and z are said to be direction ratios of vector A. These are scalar components, and these scalar components are also said to be direction ratios of vector A. Then unit vector in the direction of vector A, unit vector in the direction of vector A is denoted as a cap, this symbol cap. It is obtained by multiplying vector A by 1 upon its magnitude. So 1 upon magnitude A times vector A. In short, this is also written as A cap is vector A multiplied by 1 upon magnitude A. So it is unit vector in the direction of vector A. Unit vector in the opposite direction of vector A is now in the opposite direction. So change sign of this vector, minus A upon magnitude A. Vector of magnitude K, vector of magnitude K in the direction of vector A. This is unit vector in the direction of vector A. Now in the direction of vector A, we need vector of a magnitude K. So multiply this by K. So K times A cap upon magnitude A. And unit vector, vector of a magnitude K in the opposite direction. In the opposite direction of A is minus K times A upon magnitude A. This is unit vector in the direction of vector A. If you change sign, it remains unit, but direction is opposite. If you multiply this by K, direction remains change, but magnitude is K times. Similarly for minus K. Then see, if L, M and N are direction cosines of vector A, if L, M, N are direction cosines of this vector A, L means what? Cos alpha, M means cos beta, N means cos gamma, where alpha, beta, gamma are direction angles of this vector A bar or vector A. So if L, M, N are direction cosines of vector A, then L times I cap plus M times J cap plus N times K cap. This is unit vector in the direction of A. So it is unit vector in the direction of vector A. So whenever direction cosines are found or given, multiply direction cosines or take direction cosines as scalar components. So it is unit vector in the direction of that vector. Then vector, if lambda is positive, then vector A and lambda times A, these are in the same direction. These are in the same direction. If lambda is negative, then vector A and lambda times vector A, these are in the opposite direction. That means for any lambda which is non-zero, vector A bar and lambda A bar are either in same direction or opposite direction. So these vectors are collinear vectors. These are collinear vectors. Then if vector A is xi, yj, zk, this is vector A, then method to find direction cosines, cos alpha equal to, cos alpha can be found by x upon magnitude A cos beta is y upon magnitude A, and cos gamma is z upon magnitude A. Or if you say this vector is R, so keep your symbol R. For vectors we can use any symbols, vector R, vector A, vector B, vector X, vector U, V. So to find direction cosines of any vector, method is divide scalar components by magnitude. So then these are direction cosines of vector R bar. And from direction cosines, alpha is cos inverse x upon magnitude R, beta is cos inverse y upon magnitude R, gamma is cos inverse z upon magnitude R. These are direction angles of vector R. So this is about direction cosines and direction angles. Method to find direction cosines and direction angles if any vector is given. Then next point is vector joining 2 points. Vector joining 2 points. Vector joining 2 distinct points. Say in the space, this is x, this is y, and this is z. In the space, suppose that this point is P, whose coordinates are x1, y1, z1. This point is Q, whose coordinates are x2, y2, z2. These are distinct points. Then how to find vector PQ? This is vector PQ. So method is, say here P x1, y1, z1 and Q is another point whose coordinates are x2, y2, z2 are 2 distinct points. In R cube. That means in space. Then vector joining P and Q, that is vector PQ, it is equal to, say P is initial point, Q is terminal point. So from terminal point I am taking subtraction of scalar components. Q is terminal point, so x2 minus x1 times I cap, y2 minus y1 times j cap, z2 minus z1 times k cap. This is vector PQ. Difference of scalar components we set with I, j and k. But difference of scalar components in which order? Terminal point minus initial point. Terminal point minus initial point. Terminal point minus initial point. Take numbers from terminal point, subtract initial point. So that is vector PQ. And its magnitude is, magnitude of this vector is square root of square of this number plus square of this number plus square of this number. Now because of square we can change order of this difference. So we can put here x1 minus x2, y1 minus y2, Z1 minus Z2. We can change order of difference because of square. Sign remains, value remains unchanged. Or simply we can also keep as it is, x2 minus x1, y2 minus y1, z2 minus z1. Keep as it is, no problem. So that is magnitude of vector PQ. As for example, if P is 3 2 minus 1 and Q is 4 minus 5 0, then vector PQ is, say terminal point is Q. So from terminal point take take subtraction. So 4 minus 3. So 4 minus 3 is 1. So 1 times I cap plus minus 5 minus 2, that is minus 7 times j cap plus 0 minus minus 1, that is plus 1 times k cap. So this is vector PQ and its magnitude is square root of 1 square is 1 minus 7 square is 49 plus 1 square is 1, so root 51. So it is about a vector obtained by joining two distinct points. Then next point is section formula. Section formula. Say if suppose position vector of point A, position vector of point A is vector A. Say showing this diagram in detail. Suppose in a space here, this is x-axis, this is y-axis, this is z-axis. Here I am taking a line segment AB. Position vector of this point is vector A. That means joining A with origin, this vector is vector A. Similarly, this vector joining B with origin, this vector is vector B. So if position vectors of A and B are vector A and vector B, we want to find a point, position vector of a point dividing this line segment AB in ratio m is to n. Then formula is, here I am writing formula, position vector of a point P dividing line segment AB in ratio m is to n. Position vector of a point P dividing line segment AB. Here we are dividing internally. Word I insert internally. Internal division in ratio m is to n, where A bar and B bar are position vectors of A and B respectively, is, so position vector of P is R bar is equal to mb bar plus na bar upon m plus n. Section formula: mb bar plus na bar upon m plus n, that is position vector of this point P if P divides internally in ratio m is to n. If P divides externally, if P divides externally in ratio m is to n, then position vector of P will be, suppose P divides externally, that means P does not lie on line segment AB, it lies somewhere here. So if location of P is here, that means external division. If P is here, this is for external division. Then position vector of this point is, we change this sign, mb bar minus na bar upon m minus n. So this is section formula. Now see questions from exercise. First question is, find magnitude of vector A 1 by root 3 times I cap plus 1 by root 3 times j cap minus 1 by root 3 times k cap. Say here magnitude of vector A, by definition we take square root of sum of square of scalar components. So square root of sum of square of 1 by root 3 plus 1 by root 3 square plus minus 1 by root 3 square. Square root of sum of square of scalar components, that is magnitude. So it is equal to square root of 1 by 3 plus 1 by 3 plus 1 by 3. So this is 1. Now write two different vectors. See, word is different vectors having same magnitude. Suppose we take vector A. Suppose I am taking vector A 2i minus 4j plus k. This is vector A. Now first of all I find its magnitude. So its magnitude is 2 square is 4 plus minus 4 square is 16 plus 1 square is 1. So it is root 21. This is vector with magnitude root 21. Now we want another vector B such that its magnitude is also root 21 but different from this vector. So suppose I put here 3i. If I keep here 3i, then I should keep here 9. Then I keep minus j, then I should keep minus 1 square, that is 1. So 9 plus 1 is 10. Now still how much is left to be 21? Here we want 11. 10 plus 11, 21. So to have here 11, we should keep here square root of 11 times k. So these are vectors. These are required vectors whose magnitudes are same. So here magnitudes are same. Now find x and y so that these two vectors are equal. Given that these two vectors are equal, so x times I cap, x times I cap, y times j cap, this vector and this vector are equal vectors. If two vectors are equal, then both the sides compare scalar components. So comparing scalar components, x is equal to 2 and y is equal to 3. Next question, find scalar and vector components of the vector with initial point 2 1 and terminal point -5 7. Suppose that this point is A, initial point 2 1 and terminal point is -5 7. So we want vector EB. A is initial point, B is terminal point. So vector EB, now vector from two distinct points, the procedure is, what we do, from terminal point we subtract initial point, terminal minus initial, so terminal minus initial, so -5 -2 times I cap, then plus 7 -1 times j cap. There are two components in each point, that means these are points in R square. So this vector will be in R square. So there will be two vector components, vector component with I cap and vector component with j cap. If in given points there are three components, that means points are in space. Then you should add here one more k cap component. So vector AB is -7 times I cap, 6 times j cap. So scalar components are here, scalar component of these vectors are -7 and 6. These are scalar components, and vector components are of this vector are -7 times I cap and 6 times j cap. These are vector components. Then here, find the sum of factors, vector A, vector B and vector C. We want sum of factors A, B, C, that is I minus 2j plus 1k plus minus 2i plus 4j plus 5k plus I minus 6j minus 7k, vector A plus B plus C. It is equal to, say this is 1i minus 2i plus 1i, so I plus I, 2i minus 2i, that is 0i, plus minus 2j plus 4j is plus 2j, 2j minus 6j, that is minus 4j, k bar or k cap plus 5 times k cap, that is 6, 6 minus 7 minus 1k minus 1 times k cap. So this is simply denoted as minus 4j plus minus 1 times k cap. This is required addition of factors. Here we want a unit vector in the direction of I plus j plus 2k So to find unit vector in the direction of given vector, first of all we find magnitude. Magnitude of this vector is square root of 1 plus, say here scalar component 1, so 1 square is 1 plus 1 square is 1 plus 2 square is 4, so that is root 6. Now unit vector in the direction of vector A is, notation is A cap and formula is multiply that vector by 1 upon magnitude A. That means 1 upon magnitude A, so 1 upon, what is magnitude A? Root 6 times A cap. A cap is vector A. This is value of magnitude of A. Now vector A is I plus j plus 2k. This can be also expressed as 1 by root 6i plus 1 by root 6j plus 2 by root 6k. This is required unit vector in the direction of vector A.